Hello, good morning. I am Khaja Asifullah, lecturer in chemistry from Government Degree College, Falaknuma, Hyderabad. Today, I will discuss about the atomic structure. It's the sixth part of the series in which we are discussing atomic structure or different topics of atomic structure. In the previous class, we were discussing about the quantum numbers, and we know that there are four quantum numbers: principal quantum number, n, azimuthal quantum number, and L, magnetic quantum number, m, and spin quantum number, s. Of these four, in the last lesson, or part 5th, we discussed three main quantum numbers, n, L, and m, that is principal quantum number, azimuthal quantum number, and magnetic quantum number. Today, we will take first the fourth spin quantum number, or fourth quantum number called as spin quantum number. It is denoted by S. It was proposed by Uhlenbeck and Goldschmitdh. It explains about the magnetic character of an electron. It gives the spin of an electron on its own axis. You should remember that the magnetic properties of an atom or an element, a molecule or compound depends upon the spin of electrons on their own axis. In other words, when electron spin on their own axis, they produce a magnetic field or magnetic moment. This is because we sometimes consider electron as a tiny magnet. Now, coming back to the quantum number S, it gives the spin of electron on its own axis. Also, the direction in which the electron spins, because there may be two directions. Therefore, we assign two values for spin quantum number S, and the values are plus half and minus half, 1 by 2, 1 by 2, with two different signs, plus half and minus half. And we also know that every orbital can accommodate two electrons. When two electrons belongs to the same orbital, they are called paired electrons, and the spin of paired electrons will be in opposite direction. That means one electron will spin in one direction called as clockwise direction. Then the other electron spins in opposite direction or in anti-clockwise direction. Hence, two different values are assigned, and these are plus half and minus half. Now, electrons of same orbital are paired, and they have or repulsion between them due to same charge. Why? Because we consider electron as a negative particle, or it is a negatively charged particle. And also, just now we heard that the electron may be considered as a tiny magnet, or when it spins on its own axis, it produces some magnetic moment. And since electrons belong to same orbital, will produce same magnetic moment with different or opposite sign. Therefore, there will be some force of attraction between these two electrons due to opposite magnetic moment. But you should remember that the repulsive force or force of repulsion will dominate the force of attraction. The repulsive force or repulsion is due to similar charge on electron, and force of attraction is due to magnetic moment they produce in opposite direction. So repulsion between two electrons dominate. This figure illustrates how the electrons spin. Here, this electron is spinning in clockwise direction. We are assigning minus of value for S, or spin quantum number. This is in anti-clockwise direction, and we are assigning plus of. Same is the case with this figure. This figure also illustrates the same thing. Spin quantum number can also be denoted by ms. That means those two symbols are there. Either you can represent it with S or ms. This is anti-clockwise direction, plus half for the quantum number, and this is clockwise direction, minus half. Now, this figure illustrates that when electrons spin on their own axis, they produce some magnetism or magnetic moment, because the direction of the spin is opposite. So they produce the magnetic moment of with the same magnitude but with a different sign or opposite sign, positive and negative. Therefore, the total or resultant magnetic moment of paired electron will be zero. Or in other words, the magnetic moment produced by two electrons belonging to same orbital will be zero. Resultant magnetic moment will be zero for them. Now, after having the knowledge of all four quantum numbers, namely principal quantum number n, azimuthal quantum number L, magnetic moment, magnetic quantum number m, and spin quantum number s, now we will be able to identify an electron present in an atom on the basis of values of these quantum numbers. For example, if we take a case where the value of n is 3 and the value for L is 2, and m can have values from -2 to +2, whereas for S, that is spin quantum number, the values is plus half. Now you can have information from above as follows. Because the value of n is 3, means the electron belongs to third orbit or third main energy level. And then the value of azimuthal quantum number 2 will give you the knowledge that it belongs to d sub energy level. And values of m, that is magnetic quantum number, says that there are 5 orbitals from -2 to +2, means -2, -1, 0, +1, +2. Okay. Now every d orbital, how many d orbitals are there? 5 in total. Every d orbital has 1 electron each. Why? When we have 5 electrons and 5 orbitals of same sublevel, these are called degenerate orbitals, and they will be having 1 electron each. Means we can assign one value for spin quantum number. This gives you an idea that all are unpaired electrons in d sublevel. Similarly, opposite to that case, that means we can write quantum numbers for a given electron. For example, if we have 4s2 electrons, then we can write the quantum number values for quantum numbers n, l, m, and s as follows. Here 4s2. 4 means the value of n, that is principal quantum number, means n is equal to 4. Since it is s sublevel, therefore s sublevel means L will be having value 0, or it belongs to s sublevel. And in s sublevel, we have s orbital, because when L is equal to 0, we will be having m is equal to 0. Means both L and m will have value 0. And in that orbital, 2 electrons are there. Therefore, we can assign plus half and minus half to them. So in total, there are 2 electrons in 4s orbital. From that example, we can say that both the electrons belong to fourth energy level. In that, the sub energy level is s, and orbital is also s orbital. And since there are 2 electrons in that s orbital, therefore one will be having minus half value for spin quantum number s, and the other will be having plus half as the value for s, that is spin quantum number. Now we have here in this table 4 quantum numbers given by n is equal to 1 to 4 quantum numbers n, l, m, and s. Here we are taking the values for n as 1, 2, 3, 4, means this is first energy level or first orbit. N is equal to 2 means second energy level or second orbit. Similarly, third orbit, fourth orbit. Now, when n is equal to 1, L can have only one value and it will be 0. And when L is equal to 0, I told you that M will be 0. So L is equal to 0 means M is equal to 0, and it will be 1s orbital, means sub energy level is s, orbital is also s, therefore it is 1s. And in 1s, if there is one orbital, therefore it can accommodate not more than 2 electrons. Therefore, in first orbit, there will be not more than 2 electrons. And that first orbit or first shell is called K shell. So the capacity or size of first shell or K shell is to have only 2 electrons. Now, in the case of second orbit, we will be having n is equal to 2. That is, the value of n is 2. And here L will be having two values, and that is L is equal to 0 and L is equal to 1. Again, for L is equal to 0, M will be 0, and this will be S sublevel and S suborbital belonging to second orbit. Therefore, we write it as 2s. Again, there can be 2 electrons because it has only one orbital. Coming to the second value of L, that is equal to 1, we will be having the values for M, that is magnetic quantum number, as -1, 0, 1. That is, when L is equal to 0, M will have three values: 2 into 1 plus 1. 2 into 1, 2 plus 1 means three values. And these values start from -1, 0 and ends at 1. Means there are three orbitals in that sublevel, which is given by L is equal to 1, means P. P sublevel having three orbitals. Every orbital can accommodate 2 electrons. 3 into 2, 6 electrons. And therefore, the second orbit or second main energy level or L shell will have 2 plus 6, 8 electrons. In third orbit, there will be three values for L: 0, 1, and 2. For L is equal to 0, again M will be 0, and it will be called as S sublevel and S suborbital. It belongs to third orbit, therefore we write 3 for all these. Now, for L is equal to 0, S. For L is equal to 1, P. Now, for L is equal to 2, it will be 2 into 2 plus 1 is 4 plus 1, 5 values ranging from -2, 1, 0, 1 to 2. Means the least value for M is -2 and highest value is +2 when L is equal to 2. Now, this L is equal to 2 gives you sub-energy level D. In D sub-energy level, we will be having 5 orbitals, D orbitals, 5 D orbitals. And every orbital can accommodate 2 electrons, therefore 2 into 5, 10 electrons. Now, total number of electrons in third orbit, that is M shell, can be 2 plus 6 plus 10, 18 electrons. And in the fourth shell, and you go beyond that, generally we have 4 values for L. We can have more than 4 values for fifth orbit, that is fifth, 5, 6, etc. But generally we take up to F sublevel only, because for elements which are discovered or we know till today, this is the last sublevel we require, not beyond this. So in fourth orbit or fourth main energy level, which is called as N, we will be having 4 values for L ranging from 0 to 3. For 0, M is equal to 0 and it is 4s orbital, and there will be 2 electrons. L is equal to 1 means there are 3 orbitals in P sublevel called as 4p. And 3 into 2, 6 electrons. Similarly, for L is equal to 2, 5 values for M from -2 to +2, 5 into 2, 10 electrons. Now, coming to the L value 3 for L, 3 into 2, 6 plus 1, 7 values, starting from minimum value -3, -2, etc. up to +2. +3 actually, 3 is not written here. So there will be 7 values: -3, -2, -1, 0, 1, 2, and 3. So there will be 7 orbitals in F sublevel. So 7 F orbitals can accommodate 14 electrons, 7 into 2, 14. Now, if you sum it up, 2 plus 6, 8 plus 10, 18 plus 14, 32. So, nth shell or fourth orbit or fourth main energy level can accommodate 32 electrons. With that, we end the topic of quantum numbers, which give you an idea of energy levels, sub-energy levels, orbitals, and number of electrons in different shells and subshells and orbitals around the nucleus in an atom of an element. Now we will switch over to the topic called as electronic configuration of elements. Then what it is? Actually, it is the arrangement of electrons. It is the arrangement of all electrons present in an atom of a given element in different orbitals and in increasing order of their energy levels. Now, standard notation. When we write electronic configuration, we have to consider a standard notation. It is nothing but NLX. Again, this N is nothing but principal quantum number, and value of principal quantum number will be written here. L is azimuthal quantum number. According to the value, we write the sub energy level or orbital here, like SPDF 1, 2, 3, 4, etc., SPDF, etc. And X is nothing but number of electrons present in that sub-level, like 0, 1, 2, 3, etc. An orbital can have 0 electron, means it is empty. 1 electron, half filled, 2 electrons, completely filled, like that. So it is standard notation, NLX. Here, there is an example like 3D5, 4S1, means there are 5 electrons here in 3D orbital or 3D sublevel. Here 1 electron in 4s. Now, to write electronic configuration, we need atomic number or Z of an element. Atomic number is denoted by Z, and it is equal to number of protons present in an atom of an element, which is generally equal to number of electrons in an atom around the nucleus for a neutral atom, not for ion. So generally we define atomic number as number of protons. Now, to write electronic configuration, beside the symbol of element and atomic number, we require certain rules which we have to follow. And these rules are: first is Aufbau principle. Second is Hund's rule. Third is Pauli exclusion principle. And fourth is stable electronic configuration, that is called as half and completely filled sublevels. And fifth one is N plus L rule. There are 5 principles and rules totally which we have to follow while we write the electronic configuration of a given element, beside knowing the remembering the atomic number and symbol of that particular element. What are they? First one is called as Aufbau principle. Second is called Hund's rule. Third is called Pauli's exclusion principle. Fourth is half and completely filled electronic configuration of sublevels, and fifth is N plus L rule. Now we will take one by one. First one is Aufbau principle. Aufbau principle is nothing but building up. So here we arrange the orbitals, different orbitals in order of their increasing energy. So what this principle says? It says that the orbitals or subshells which have least energy will be filled first with electrons. According to Aufbau principle, electron will enter first into those orbitals which have least energy. And when we write the order of electronic configuration, or order of orbitals with respect to energy, the order will be like this: 1s has least energy, therefore it comes first, then 2s, then comes 2p, 3s, 3p, 4s, 3d, and so on. This order is based on the increasing energies of these orbitals. This chart or diagram shows the energies of different orbitals. This is energy. It is taken on y-axis, means it increases from bottom to top. Above, it will increase. So here, when we plot a graph, then one S will be in the bottom, at the bottom, or it has least energy. So it will come first. Then if we compare these four orbitals, three have same or similar energies, which belongs to 2p sublevel. These are called degenerate orbitals. Now, among these four, 2s is having some less energy. 2s has less energy than 2p, therefore it comes first. So after 1s, we will write 2s, then 2p, because above 2p, we have 3s, not below or just equal to that. Therefore, after 2p, we will have 3s, then comes 3p, then comes 3d. Now, when compared, when we compare these two, 4s is having some less energy than 3d. Therefore, after 3p, we will take first 4s, and after filling this 4s only, we will start filling the electrons in 3d. After 3d, if it is completely filled, next electron will enter into 4p. This diagram, which is generally called as Moeller diagram, help us to remember the orbitals with respect to their energy, and we can write increasing order of energy for orbitals. 1s, then 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 4p, after that 5s. After 5s, 4d, 5p, 6s, then 4f, 5d, 6p, 7s, 5f, 6d, 7p, then 8s, like that, and so on. This chart again give you an idea of orbitals having energies and their in order in increasing energies, or increasing order of their energies. Here 1s, then 2s, 2p, 3s, 3p, 4s, then comes 3d. After 3p, we cannot write 3d. First we have to write 4s, then 3d. Why this happens, we will discuss in next topic, called as N plus L rule. So we will be having 3D, then 4P, then 5S, and so on. Here, 1 means first energy level, or first orbit, 2 means second orbit, third orbit, fourth, fifth, up to 8 orbits. Second rule is called Hund's rule. Hund's rule says that pairing of electrons in degenerate orbitals will not start until and unless all degenerate orbitals are half filled. Just now I gave you the definition of degenerate orbitals, or what are degenerate orbitals. Degenerate orbitals are those orbitals which have nearly same or equal energies. So when we have degenerate orbitals in an atom of an element, they have to be first half filled, then only pairing of electron in those degenerate orbital starts. For example, if we take carbon, the symbol of carbon is C, and 6 is the atomic number of carbon. The correct way to write electronic configuration of carbon is 1s2, 2s2, 2p2. But in 2p2, we have 3 different orbitals, namely 2px, 2py, and 2pz. Therefore, when we write the electronic configuration, these are called degenerate orbitals, and they have to be half filled first. Means 2 plus 2, 4 electrons are accommodated in 1s and 2s. Then fifth and sixth electron will be accommodated in 2px and 2py, 1 electron each, and the 2pz orbital will be empty, and there will be no electron in it. This is the correct way to write the electronic configuration for carbon atom. But if we write 1s2, 2s2, 2p2 as it is written here, that is 2px2 and 2py0 and 2pz0, it is wrong, because 2 electrons are entered into 2px means it is paired. So it is incorrect. The same thing is shown here in this figure. If you go through this figure carefully, how many electrons are there in total? 2 plus 2 plus 2 is 6. Again, it is the carbon atom. We are writing electronic configuration for carbon element, carbon. So it has 6 electrons, and we can write 2 plus 2, 4 electrons in 1s and 2s level. The fifth and sixth electron should be unpaired, and they should go into 2 different orbitals of p level or p subshell. Okay, we cannot write both the electrons in one orbital of p sublevel. It is incorrect to write like this. It is correct. Why? It is in accordance with Hund's rule, which says that pairing of electrons in degenerate orbitals start when all degenerate orbitals are half filled. Otherwise, it will not start. So, if seventh electron is there in the case of nitrogen, again it will go here. Then only in oxygen the pairing will start. So, this figure or table illustrates that. If you consider carbon, it will have 1 electron in 1p orbital, 1 electron in another, the third one is kept empty. And here in nitrogen, in the case of nitrogen, 3 unpaired electrons are there in 3p orbitals. Now in case of oxygen, 8th electron will enter here in one of the p orbitals. So pairing start here. Why pairing starts here? Because every degenerate orbital of p subshell is having one electron each or half filled. Next, in fluorine, second p orbital will be paired, or it will be having two electrons, and in neon, all p orbitals are completely filled. So p sublevel is completely filled in neon. Now, the third principle, which is called as Pauli exclusion principle. Pauli exclusion principle says that no two electrons in an atom can have all four quantum numbers same. What are the quantum numbers? Principal quantum number n, azimuthal quantum number L, magnetic quantum number m, and spin quantum number s. The values for all those four quantum numbers for any two electrons cannot be same. Then if three have same values, then fourth quantum number at least should have different values. So this principle says that no two electrons in an atom can have all four quantum numbers same. If three are same, then at least fourth will be different. For example, we are taking here 1s2 electrons. If we write quantum numbers for 1s2 electrons, we can understand the principle easily. Here 1s2 means there are two electrons in the s sub level and s orbital of first orbit or first main energy level. Because in first 1s orbital we have two electrons, namely first electron, second electron. So n, value of n is 1. Why? Because it is 1s means first orbit. And when n is equal to 1, L can have only one value, and that is 0. And when L is equal to 0, M can have value 0. And here, for second electron also, the values for n, L, M are same because the second electron also belongs to 1s orbital. Then after having same values for three quantum numbers, we cannot have same value for S, that is spin quantum number. If we assign plus half to first electron, it should be minus half for second. If it is minus 1, then it is plus half, means we have to allot or assign two different values for S. Here we have two different values, plus half and minus half. Why? Because they belongs to, or both the electron belongs to same orbital, then their spin will be paired, or they will be having opposite spins. Now, we took that example in which two electrons are there in first level. Here it is the same case again, so no need to go through again. Here in second subshell, we have two electrons in s level, again the same thing, but in second sublevel, that is 2p, we will be having three orbitals, 2px, 2py, and 2pz. Here, if three unpaired electrons are there, that means every orbital has one electron, then we can assign either plus half, plus half, plus half to 3 or this, because the value for m will be different. L and n, the values for n, principal quantum number, and L, azimuthal quantum number, will be same, but the values for m will be different. One will be having minus 1, the other will be having 0, then third one will be having plus 1. In that case, we can assign plus half, plus half, plus half to all three p orbitals, or electrons present in all three p orbitals. Why? Because at least fourth one is different. So if it is completely filled, means 2p6. In the case of 2p6, we will be having for first orbital N is equal to 2, L is equal to 1, M is equal to minus 1, and S is equal to plus half and minus half. In this way, M is equal to 0 for second orbital, again two different values for S, and for third orbital M is equal to plus 1 and two different values for S. Now the fourth principle or rule which we have to follow to write the correct electronic configuration is called half filled and completely filled sublevels. Generally, if we observe the properties of elements in periodic table, especially chemical properties, we can understand that elements which are very stable and stable will have either half filled or completely filled electronic configuration. The most stable elements will have completely filled electronic configuration, as in the case of noble gases or elements belongs to 8th group or rare elements, etc. Rare gases. They have completely filled electronic configuration and they are highly stable. Why? Because they generally do not react with any other element. Therefore, their compounds are rarely known, especially except in the case of xenons, fluoride, and oxide. Generally, they do not produce compounds. Why? Because they themselves are very stable. No need to combine with other elements and to become stable. So, all elements of noble gases with general electronic configuration NS2 and P6 are highly stable. Why? Because both NS2 sublevel and NP6 sublevel is completely filled. And S means S orbital can accommodate 2 electrons. There are 2 electrons in that. And P can accommodate 6 electrons. There are 6 electrons in this. Except in the case of helium, which has 1s2, all other elements will have ns2 and p6. Similarly, for certain elements having half-filled electronic configuration, they are also stable, but less stable than noble gases. They are stable, and we can take the example of fifth group of elements, namely nitrogen, phosphorus, etc. For example, elements of fifth group, nothing but nitrogen, phosphorus, etc. They are also considered as stable. Now, if we observe that property, we can say that certain other elements also can have either completely filled all electronic configuration or half filled or mixture of these two. For example, if we take chromium and copper from D block elements, both are metals and belong to D block elements, and they are stable. They are more stable than the other neighboring elements. Then we can see or observe the electron configuration. Chromium, its atomic number is 24. Here in argon, 18 electrons are filled. So 19 to 24 means 6 electrons will enter here in this way. 5 electrons will go to d orbital, 1 electron to s orbital, which makes both orbitals or sublevels are half filled because it is stable element. So this is correct way or method to write the electronic configuration of chromium. Whereas if we write 3d4 54s2, it will be incorrect or wrong. Similarly for copper, whose electron configuration can be like this because its atomic number is 29. 18 electrons will enter into argon, and 19 to 29, that is 11 electrons will enter into next sublevels like this. 3d10 4s1. This makes it completely filled and this is half filled. So it is correct way because it is stable element. And if I write 3D9 4s2, it will be incorrect. So you have to keep it in mind. These are the special cases. Now, why they are stable? First statement, half-filled and fully filled degenerate orbitals are considered as more stable because of their chemical properties, we can say like. And second statement is extra stability is due to symmetrical distribution of electrons and energy exchange or exchange energy. This is half-filled. P half fill means P has three, P sublevel has three orbitals and all orbitals are having one electron each. Therefore, half filled, this is two electron each means completely filled. This is half filled P orbital, half filled D orbital. This is completely filled P orbital, completely filled D orbital. For in the for example, in the case of noble gases, P6 completely filled. For elements like zinc, cadmium, mercury in from D block elements, it is completely filled for D sublevel. Now the last rule which has to be kept in mind while we write the electronic configuration means we have to follow these rules to write the correct electronic configuration. If we do not follow these rules, there may be some mistake while we write the electronic configuration. This is the fifth in series. Now, this is called N plus L rule, where N is quantum number, principal quantum number, and L again quantum number called as azimuthal quantum number. The value, sum of the values of these two will be taken into consideration here. Now, according to this rule, orbital with lesser value of for n plus L will possess lesser energy and it will be filled first. The orbital which has least value for n plus L will be filled first with Y because it has less energy. Now, n is the value for principal quantum number and L is the value for azimuthal quantum number. Again, we have to take example as this. We have to compare. Therefore, we are taking two orbitals. Okay. When we take two or more orbitals, then only we can compare. So here 3D and 4s are taken. For 3D, the value of n is 3 and value of L, that is because it is D sublevel, it will be 2. The sum is 3 plus 2, 5. Whereas for 4s orbital, the value of n is 4 and value of L is 0. Therefore, 4 plus 0 means 4 only. If we compare the values of n plus L for 4s and 3D, it will be 4 for 4s and 5 for 3D. Therefore, we can say that 4s orbital has lesser energy than 3D. Why? Because its n plus L value is less. This table shows you the values. For 1s it is 1, 2s 2, 2p3 in this way. So we can arrange the orbitals in increasing order like this: 1s, 2s, 2p, 3s. Here comes the problem. Both the orbitals are having same value 3, 3. But here you see this has lesser value for n, therefore it is placed first. It will be placed first. So in order 1s, then 2s, then 2p, 3s, like that. 3p, 4s, 3d. So here 4 values for these two, 5 for this. Again here n value for n is less, therefore it will come first, then this, like that. So ultimately the order of orbitals with respect to energy are in increasing order of their energies is again 1s, then 2s, 2p, 3s, 4s, 3d. Means up to these orbitals there will be many such orbitals, if you go on after 3D, 4P like that. Here, among these, 1s has the least energy and will be first or filled first. So always we have to take it first. Then this, if it is also filled, then this. It is also filled, then this, like the. With this, we end the lesson here. Thank you, one and all, for watching. Thank you.